So, in the last class we have briefly started what a lattice is, right. So, we are going from so we have deviated a bit from looking at just point symmetry operations. We are now looking at lattice. We have introduced the idea of lattice having translational periodicity or translational symmetry, right. So we said any collection of abstract collection of points which are periodic in nature, right. So, is a lattice, and we have mathematically seen how to express a lattice as just summation of various delta functions at all the lattice points, and all these lattice points are related by a translation, right. Okay. So, now so let me define certain other aspects which are going to be important. The first one is what is called a unit cell, right. So, I have a lattice now. So, from now on I am just going to assume that everyone knows what a lattice is. I have a lattice which is somewhat like this, a 2-dimensional lattice, a set of points, right. Now, since there is translation, right, so every time I do not need to draw all these points, right. So, since there is translational symmetry and there is some periodicity, what I can look at is I can look at a unit of this lattice which sort of represents the properties of the entire lattice, right. So, I can just understand the properties by looking at just one particular unit. Okay. So, the diagram did not come out quite well, so I will draw it again. So, then there is that, 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 there is that. Right. So, a fundamental unit of this, right. So, for example, so I can select this as my unit, right. So, I am going to select one of these units, right. I keep on repeating this unit and I can generate the lattice. It is not just repeating the unit, I am going to calculate all sort of electronic properties of this material within this unit cell, right, and I am going to impose some sort of periodic boundary conditions, because this unit periodically repeats, right. And by periodically repeating this unit I can regenerate the entire lattice, right. So, ad infinitum. Okay. So, that is one of the unit cells that I can select, but so this is called a unit cell. But by no means is the selection of a unit cell unique, right. Now, this unit cell has so the question arises, how many lattice points does this unit cell encompass, right. So, the way to count that is, okay, so this unit cell is going to encompass 1/4 of this lattice point, 1/4 of this lattice point, 1/4 of this lattice point, and 1/4 of this lattice point, right. So, that is how I am going to count. If I am sharing one unit cell between so if the unit cell passes through the lattice point, that lattice point is shared with other unit cells also. There will be one unit cell on this side, one unit cell on this side, and one unit cell on this side. So, this lattice point is shared between 4 unit cells. So, I am just going to give 1/4 to each of these unit cells, and I am going to say that this unit cell has 1/4 the lattice point. So, the total number of lattice points in the unit cell of interest in my unit cell UC1, in UC1, total number of lattice points equal to 1. So, that is a complex way of doing things. The other simpler way of doing things is so instead of looking at UC1, I am going to shift UC by a certain extent, just translate it, right. So, UC1 is translated to UC2, both of them are exactly of the same dimensions. UC2 is just UC1, which is translated a bit, not by a lattice vector, translated by less than lattice vectors. Okay. Then UC2 clearly encompasses only one lattice point. Okay. Now, the choice of unit cell that lets you encompass only one lattice point, the unit cells in which there is only one lattice point are what are called primitive unit cells. Okay. Now, I can sort of draw some primitive unit cell which is some other primitive unit cell which is not that obvious. So, for example, I draw these two, that is also so I can define a unit cell that way, right. So, that is also a primitive unit cell where I can fill up the entire space with this unit cell, right. So, I can generate the periodicity of the lattice with this unit cell, and there is one lattice point inside this unit cell. Okay. Now, if there is a primitive unit cell, there can be so this is UC3, let me just name this as UC3. Okay. There should be a non-primitive unit cell. Non-primitive unit cell is that unit cell which encompasses two not more than one lattice point. So, we will define non-primitive unit cells for a reason that I will discuss in the next class or the class after. But for example, if I define this to be my sorry, I remove that, I come back to a green pen now, and then if I am going to define this, sorry, I have to select green. If I define this, right, so as my unit cell, right, this is encompassing, this is unit cell 4, and my unit cell 4 encompasses two lattice points. And this is a non-primitive unit cell. It makes sense to sometimes define certain unit cells and certain non-primitive unit cells. We will actually look at why that is the case very soon. But so for now we will just define that we will just make it a point in our heads that there are primitive unit cells and there are non-primitive unit cells, and the definition of unit cell is not unique. You can define unit cell any which way you want to. Okay. But there are some constraints that come up because of symmetry. As a result, defining a unit cell in a certain way will preserve the symmetry of the system, and that is what is a preferred way of defining unit cells, but that we will see later. Okay. So, that is a unit cell. Now, there is a lattice, right. So, there is a lattice which is just a set of abstract collection of points, right, on this lattice, right. So, lattice I said is just a template, right, but on a periodic template you should put something, right, and that something can be atoms, right. So, I can put a couple of atoms here, right. With respect to every lattice point I am going to put a couple of atoms like this, right. So, a dumbbell of atoms, right. So, something like this. The lattice point really does not exist, but when I do an electron microscopy experiment, I do not really see this abstract collection of lattice points. What I see are these dumbbells, right. So, what I see are the atoms, and their arrangement, right. So, these are real things, right. So, what you put this single unit that you are putting, okay. So, with respect to a lattice point where lattice acts as a template, and with respect to that template I am putting this single unit, in this case of a dumbbell of atoms, right. So, it can be whatever atom it is, right. So, that is what is called a motif, right, or some people call it basis, but this is not to confuse with basis set of in mathematics, right. So, that is so if I have a coordinate system, I say A, B, C are my basis vectors, right. So, this is not the same basis, this is a set of asymmetric unit that you put at a lattice position. Now, basis does not need to be atoms, right. So, I can put a basis of spiders or motif of spiders or motif of buffaloes, right. So, I can have a buffalo lattice, for example, right. So, at the at different lattice positions I put buffaloes and arrange them periodically. I have a structure of buffaloes, not lattice of buffaloes. In all these different lattice positions I put buffaloes. Okay. Now, so for I just need to caution a bit about these definitions. So, for example, you may have heard things like, okay, so first let me define what crystal structure is and then come to cautioning. So, then comes the actual definition of what a crystal structure is. So, I have lattice now, which is a template, and on this template I am putting my motif. My motif is a small buffalo or whatever this object is, right. So, with respect to the lattice point, I exactly know how far this is going to be, but I am just going to periodically repeat my template everywhere along the lattice point, and so on and so forth, right. So, this entire thing which combines a motif and a lattice is what is called crystal structure. And typically, since we are talking about crystals of different elements, this motif is a set of atoms. Okay. It can be single atom or a set of atoms, right. So, or a molecular motif, right. So, I can have an H2O solid, ice solid which have H2O units, right. So, H2O will be a motif, okay. Set of atoms or a molecule, okay. Now, so what is this combination? How do I combine a motif and a lattice? So, for example, I am going to say motif is my B of R or basis, right. So, B of R just defines, so with respect to the origin, right, I am going to say that I have two atoms which are here, right. So, this is so the shape of these atoms, the exact spatial extent, etc., is defined by B of R. B of R is one function which defines this motif. Okay. Now, the operation that I do to create a crystal structure from lattice and motif is what is called a convolution, crystal structure. Okay. So, mathematically a convolution operation tells me what a crystal structure is. So, what is for example, a structure, a crystal structure C of R is nothing but lattice L of R convoluted, there is a convolution operation with B of R. Okay. Now, L of R is your delta function, delta U minus U delta R minus U R U V W. These are all at different lattice points. Okay. Now, B of R is just your motif, right. So, it can be a spider, it can be this set of two atoms, right. So, this is the real function that discusses the the fundamental unit that is periodically repeating according to the template of the lattice. Okay. So, and this sort of a so the operation that I just did, right. So, I put the lattice points, and with respect to the lattice points, right. So, considering all the lattice points as my origins, I add in a couple of atoms, right. So, okay. So, this operation that I did, this is convolution. I am not multiplying these two, I am convolving these two. Okay. So, then when I actually image it, I am not going to look at the lattice points because they are just abstract quantities. What I am going to look at is your some sort of a structure like this. So, this is what is called a crystal structure. To put it in words, it is motif periodically arranged on the template of lattice, right. So, motif periodically arranged on the template of a lattice. Okay. Now, essentially, since I use the word convolution, it is important to define what convolution is. We will come back to convolution later on when we are actually looking at properties in time domain, right. So, so then we will actually look at convolution in more detail, but so two functions, if I am convolving two functions, f of r is convolved with g of r, this operation is nothing but f of r prime times g of r minus r prime d r prime, and the r prime goes from minus infinity to plus infinity. Okay. So, what does it mean essentially? So, it means I will just show you in this presentation. So, I have a function f, right. So, which is sorry. Let me use this. Okay. So, I have a function f, right. So, which is in so asymmetrically defined, right. So, f is not a symmetric function about x equal to 0, right. So, it is there is this small bump here, right. I have a function g which is like this, right. So, when I do the convolution operation, what I do is first I do g of r minus r prime, right. So, there is a minus r prime. So, g sort of gets inverted or mirrored about the y axis, okay. And what I am doing is I am trying to slide g over f, right. So, I am going to slide g over f and look at the overlap integral, right. When then I point, I write what I plot what is the value of that integral at every r, right. So, essentially if my overlap is just this much, so that is the area under integral, that is the value at this r, right. So, and then I overlap it even more, I slide this even more, I am moving the r, and so f convoluted with g is this overlap function, okay. So, this is the simple operation of convolution, where I take a function g, I invert it, right. So, or I mirror image it about the y axis, I take minus g in some sense, and so I pass minus g over f and I look at the overlap integral or the right. So, between f and g, and that overlap integral is my convolution at that time or at that point r, okay. So, this is and so you get a function like this, okay. Similarly, I mean there is another operation called cross correlation, where you do not actually take minus g, you take only plus g, and then you directly start sliding this triangular entity over this this function f, right. So, and then you look at the overlap integral. So, that is cross correlation. These are sort of people confuse convolution with cross correlation and so on and so forth, okay. But so this is the mathematical operation of convolution. Okay, so let us come back. I'll go more in details of what convolution is later on when I actually discuss material properties. But for now, so this is a convolution operation, which means I take my motif and I slide it over over the lattice, right. So, at every lattice point, wherever there is a lattice point, the motif is there, right. So, and lattice point is also delta function. So, your integral of delta function gives you a finite value only at r equal to 0, right. So, at that lattice point, with respect to that lattice point, I put this motif, right. So, this is how this convolution operation works out, right. So, it's a simple convolution of the motif with lattice. That is what gives you a crystal structure, okay. Okay, so with that definition of crystal structure, and when I do a microscopy or X-ray diffraction experiment, all I am trying to get to is this crystal structure. So, I see the arrangement of atoms as given here. This is the arrangement of atoms, and from this I have to extract the underlying lattice, I have to extract the underlying unit cells and underlying symmetries, right. So, I have to understand what these symmetries are. So, that is how experimental problems are typically, right. So, seeing the periodic arrangement of atoms is is easy nowadays, right. So, you can see it using a high end electron microscopes, which are there in lot of places, okay. However, extracting the structure and symmetry of the periodic arrangement that you are seeing, that is the challenge, okay. So, we will formulate it a bit, and then we will be able to identify these things later on. So, okay. Then so to formulate anything, so if I am developing a language, it is always good to classify, right. So similarly crystal systems, taxonomy as they say in so taxonomy is the science of classifying objects, right. So crystal systems similarly, or crystal structures can be classified into 7 different crystal structures can be classified into 7 systems. And in this classification comes the, I mean, you may have studied something like a cubic crystal system. A cubic crystal system has so a unit cell like this, a cubic unit cell, which is defined as so cubic is more famous one, right, crystal system. So which is defined as so I have A here, I have B here, so this is A, this is B, this is C. So I am going to say A equal to B equal to C, and alpha equal to beta equal to gamma equal to 90 degrees. So I can use this as a unit cell, and my coordinate axes are can be related as so they are all equal to each other. So the unit vectors in along A axis, along B axis and C axis are equal to each other, and these coordinate axes, these basis vectors are at an angle of 90 degrees with respect to each other. Okay. So this is how you would have heard of the definitions of a cubic system, similarly tetragonal system, similarly whatever, right. But I am going to argue here that these are not primarily how the definitions are, but these are just constraints on the system that arise in the system. Right. So primarily, however, crystal systems can be defined on basis of underlying symmetry. Okay. Now what do I mean by that? And this underlying symmetry imposes constraints on the axes of these crystals. Something like A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees, right. So all these things are constraints that come up because of an underlying symmetry in the system. Okay. Now, okay, so let us first define this is x axis, this is y axis, this is my z axis. In general, they do not need to be orthogonal to each other. This is my z axis is coming out of plane, right. Now the angle between x and y is what is called as x axis or A axis. I will call this as A axis. This is B, this is C. Let me just erase this. The angle between A and B, I am going to call it gamma. The angle between B and C, I am going to call it alpha. The angle between C and A, I am going to call it beta. Okay. So these are my conventions. So angle between A and B is gamma, angle between B and C is alpha, and angle between C and A is beta. Okay. And A, B, C are my coordinate axes in general. Let me use a different color here. A, B and C need not be orthogonal. They do not need to have a 90-degree angle between them. Okay. So A, B, C need not be orthogonal. Okay. So with that, let us go to what is called a triclinic system. This is the first of the 7 systems, 1 by 7, triclinic system. Now, triclinic system is a crystal system in which there are very little number of symmetry elements. There are, you cannot have many symmetry elements there, right. So, the minimum symmetry any crystal should have, right. So, this is just by common sense, is just an identity or 1, right. So, 1 is an identity, one fold axis of rotation, which means I rotate by 360 degrees. If I rotate anything by 360 degrees, right, I should get the same object. Okay. So, this is mostly true. Let me emphasize the word mostly, because there are some phases of electrons that you have to do a 4 pi rotation, so that you get back to the original phase, but so these are ideas of topology, etc., where something similar does not work, but so mostly in all classical physics and in all crystals, right. So, I rotate a crystal by 360 degrees, I should get back the same crystal, right. So, this symmetry exists everywhere. Okay. Now, so I am not imposing so much of any sort of constraint, right. So, I can have axes where my A, B, C are sort of at whatever angle they want with respect to each other, A not equal to, and they can have whatever unit cell lengths that they want, right. So, one so one transforms x y z, or a vector x a plus y b plus z c, right, upon doing operation 1, identity operation actually goes back to x a plus y b plus z c, right. You have changed nothing. So, this sort of transformation does not impose any constraints on the axis, right. So, no constraints imposed on axis. As a result, you have A so A does not need to be equal to B, which does not be equal to C. The magnitudes of the vectors, I am just going to write it as A, B, C from now on. So, A not equal to B not equal to C, and A not equal to C, right. In general, you also do not need alpha, beta, gamma need not be equal, right. So, and to any value for that matter, and alpha not equal to gamma. So, this is a general 3-dimensional coordinate system, right. So, there is no constraints on what sort of unit cell you should select, what sort of axis you should select, etc., right. What is the relation between the axes, right. So, the unit vectors along different axes in this coordinate system, etc. So, there is no general constraints or no general relations. Okay. So, similarly, if I have 1 bar is an inversion. 1 bar is going to, if I have x a plus y b plus z c, right, by doing a 1 bar operation. 1 bar means the matrix of operation is minus 1 minus 1 minus 1 0 0 0 0 0 0, right. If I do a 1 bar operation on my vector r, right. So, I am just going to get minus x a minus y b minus z c, right. Now, again, so a vector which is so with respect to some sort of a coordinate axis, right. So, there is a vector which is at x y z transforms to minus x minus y minus z. There is no particular constraint that this transformation imposes on my vectors, right. So, to understand so no particular constraint again. It is just if I have an entity at minus x minus y minus z, I should have the same entity at x y z. Okay. So, this is inversion, and that sort of having that sort of only that as the operation in my crystal system is going to impose no constraints on the axis, right. So, my axis can again no particular constraint on the axis of the crystal system. Okay. Next, I go to what is called a monoclinic system. So, any crystal that you see that only has translational symmetry and or just an inversion symmetry as a point symmetry operation, or identity is always there, right, is by default a triclinic system, right. So and then on the top of triclinic system, if I start adding more point symmetry operations, then I get to such as two-fold axis of rotation, mirrors, etc., then I get to, you know, all these other more symmetric crystal systems, right. So one of the more symmetric crystal system than a triclinic system is what is called the monoclinic system. Okay. Now what is a monoclinic system? Let us consider one operation. So I have a two-fold axis of symmetry about 0 0 1, let us say, right. Now, if I have a two-fold axis of symmetry about 0 0 1, you know, we did this earlier, right. So I have a two-fold axis of symmetry, which means this plus actually goes to this plus, right. So x y z transforms into minus x minus y plus z, okay, and the transformation matrix is nothing but minus 1 minus 1 1 0 0 0 0 0 0, right. So I have a vector r which is x a plus y b plus z c, and this r, you know, after transforming it 0 0 1 through this operation two-fold rotation gives me minus x a minus y b plus z c. Okay. Okay. So here we are actually talking about some constraints that this is going to impose, right. So after symmetry operation, right, so my x a plus y b plus z c now became a vector, or became meaning this vector is there, this entity, so there is whatever entity is present at x y z should be present at minus x minus y plus z, right. So that is what this two-fold operation is saying, right. So this vector, right, so whatever be the you know, so if I am just taking a scalar product, right, so a dot you know, so of component of a, component along a axis and component along b axis, right. So that is you know, x a dot y b, right. So by symmetry x a dot y b in this vector should be the same as x, whatever is the x component here, minus x a dot minus y b in this vector, right. So I am just taking a scalar product, right. Now okay, so that is also, that is fine, because this is just x a x y a dot b, and that should be equal to x y a dot b. So there is this is obvious, this is you know, this is a trivial fact. Since this is a trivial fact, this does not impose any conditions on a and b. Okay. However, if I, so this does not, no conditions imposed on A and B. Okay, A and B are my crystal, the vectors of, or the basis vectors of my unit cell. Okay. However, if I take, you know, the a coordinate and the c coordinate, right, so that is x a dot z c, right, that should be equal to minus x a dot plus z c. This means irrespective of whatever is the value of x and z, right, so x z a dot c equal to minus x z a dot c. This is only possible if and only if a dot c is equal to 0. Here comes my first constraint, right. Similarly, I can do exactly, or a is perpendicular to c. If a is perpendicular to c, my angle beta equal to 90 degrees. Okay, this is my first constraint. Okay. Similarly, I can also show that, you know, x a or x sorry, y b, I am going to take b and c components, y b dot z c right. So equal to minus y b dot z c, and that also means that b dot c equal to 0, right, or b is perpendicular to c, or my alpha equal to 90 degrees. Okay. So now I have a crystal, right. So these are the two constraints. Just by having one two-fold axis of symmetry, I have two constraints, right. So now I have a crystal where I have my a axis, right. So in a unit cell, So, I am going to describe a unit cell. Now, I told you earlier that unit cell you can define it any which way you want to, but it will be nice that the unit cell captures the symmetry of the material, right. Now, in the material or in the lattice in the crystal structure, there is only one axis about which there is twofold rotation, right, and that axis is my 0 0 1, or that axis is my C axis. Okay. So, where was that? That is my C axis. So, there is twofold rotation about C axis. So, in the unit cell I will make C axis as the axis of my twofold rotation. Okay. So, I have A and then I have C and then I have a B here, right. B and C also have a 90-degree angle with respect to each other. However, A and B, right, so have an angle which is not 90 degrees, right. So, that is alpha, beta and gamma, right. So, I am going to draw a monoclinic crystal like this now. So, this is C axis, C is both perpendicular to A and B, okay. So, A and B, okay, and this angle which is the gamma is not equal to 90 degrees. The way I define it by convention, I define gamma to be greater than 90 degrees. Okay. So, if I have twofold axis of symmetry, only twofold axis of symmetry, only one twofold axis of symmetry, then my crystal system turns out to be what is called a monoclinic crystal system, and the constraints are that A does not need to be equal to B, not equal to C, and also A not equal to C, but you need to have alpha equal to beta equal to 90 degrees and gamma is greater than 90 degrees. This is by convention. So, if you define a unit cell, if your unit cell is defined this way, that also means that there is an underlying either twofold axis of symmetry or mirror also will do the same thing. If I have mirror about 0 0 1, right. So, that is going to transform my x y z to x y minus z, right. So, wherever upon transformation the sign changes, okay. So, by doing twofold axis of symmetry, I have transformed x y z to minus x minus y z, right. And by doing mirror, I have transformed x y z to x y and minus z, and I am looking at what is the the relation between the A axis, B axis and C axis. What is the angular relation and what is the the magnitude relation, right? A axis, B axis and C axis. So, this exercise just told us that wherever there is a sign change upon transformation, so x goes to minus x and z goes to plus z, right. So, these two axes, so one changes its sign, the other one does not change its sign, right. So, then A dot C should be equal to 0 or A will be perpendicular to C if upon transformation the x goes to minus x and z does not go to minus z, or x goes to plus x and z goes to minus z, right. So, only one of x and z change their sign. Okay. So, then you have a relation that A is perpendicular to C. For perpendicularity, from now on I am just going to blindly look at x goes to minus x, y goes to minus y. So, between x and y both of them are changing their sign. So, there is no perpendicularity constraint, but x goes to minus x, z goes to minus z, z goes to plus z. So, between x and z there is a perpendicularity, right. So, I am just going to look for, I am going to use this as my thumb rule and look for perpendicularity between the axis by using the above rule. And the above rule is that if upon transformation only one of x or z change their sign, then then A and C, the corresponding unit cell axis, right. X is just the magnitude of the vector along A and z is the magnitude of the vector along C. So, the corresponding unit cell axis should be perpendicular to each other. That is when that unit cell will incorporate the elements of symmetry, and the symmetry elements are twofold axis of symmetry, or in this case even mirror, right. Okay, mirror is also, by the way, 2 bar, right. So, either one twofold axis of symmetry or one 2 bar axis of symmetry will give you a monoclinic crystal system. Now, you can equivalently have twofold axis of symmetry about 1 0 0, or about 2 bar about 1 0 0, or mirror about 1 0 0. Okay. Now, that will give, since it is about 1 0 0, here gamma is not 90. So, here alpha will not be 90 degrees, but or greater than 90 degrees, but beta equal to gamma equal to 90 degrees, and A does not need to be equal to B, not equal to C. Okay. So, this is another monoclinic setting. Crystal system. Okay. Next, we look at our third crystal system out of 7, right. So, and then we stop here today. So, which is called the orthorhombic crystal system, where the underlying symmetry operation is I have not one twofold axis of symmetry, but multiple twofold axis of symmetries, right. So, I have twofold about 0 0 1, that is, and I also have twofold about 1 0 0. Okay. So, I will prove that later. If I have this and this, I will have twofold about 0 1 0, or you can, if there is twofold axis of symmetry about 0 0 1 and twofold axis of symmetry about 1 0 0, prove that there is also twofold axis of symmetry about 0 1 0. This comes by design. Okay. All right. So, if I have twofold axis about 0 0 1, about 1 0 0 and about 0 1 0. So, if I have twofold axis about 0 0 1, I already showed you that beta equal to alpha equal to 90 degrees, right. Now, if I have twofold axis about 0 0 1 0 0, I already showed you here that beta equal to gamma equal to 90 degrees, right. So, using these two, I can clearly say that alpha equal to beta equal to gamma equal to 90 degrees, and you can show that these are the only constraints. You do not have any constraints about A, B, C, A not equal to B, not equal to C. Okay. So, that is what is called and the corresponding unit cell you will define to incorporate this symmetry of at least two twofold axis, right, is what is called an orthorhombic unit cell. Rhombic, okay, or an orthorhombic crystal system, where so this is sort of like a so this is what is it called? It's called a cube, a cuboid, right. So, this is a cuboid. It is not a cube, but it is a cuboid. So, where you have A, B, C, A not equal to B, not equal to C, but all the angles, right. So, in this unit cell should be equal to 90 degrees, right. So, and this angle, sorry, that is the angle that so A and C and B and C. So, this angle, right. So, all the angles are alpha equal to beta equal to gamma equal to 90 degrees. Okay. Now, this is what is defined as an orthorhombic unit cell in lot of textbooks, but this is a constraint that is imposed because I have a 2 to 2, I have 2 or more than 2 twofold axis of symmetry. Similarly, I can have 2 or more than 2 mirrors, right. So, I can have M 0 0 1, I can have M 1 0 0, and and a twofold axis, or I can have 3 M's, right. All these things give me orthorhombic symmetry. Okay. So, yeah. So, underlying symmetry, if I have either more than two twofold axis, right. So, underlying symmetry if I have more than one twofold or 2 bar fold, axis of symmetry. Now 2 bar fold is M, right, or their combination. So, I can have 2 bar, right, something like that. That yields an orthorhombic crystal system with a unit cell, with a preferred unit cell defined that has the following constraints, and the constraints are that alpha equal to beta equal to gamma equal to 90 degrees, right. So, it is orthogonal system, right, and A does not need to be in general equal to B equal to C. Okay. All right. So, with that, let us stop here and take up the other crystal systems. We will start with the other crystal systems in the next class and go to what are called Bravais lattices, and we will see why there is a need to define what are called Bravais lattices. Okay. So, Bravais lattices and ensuing crystal systems. Okay. All right. So, let us conclude here. Thank you very much.